Before I refresh your memory on what integral calculus is, I want to tee up an application of integral calculus first. In order to do that, let's talk about the field of machine learning called supervised learning. So in the field of supervised learning, we have both an input x and an outcome y that we are predicting with our model. Our goal in supervised learning is to have a function, a machine learning function, that can approximate y using x. Examples include regression models like the clinical model of forgetfulness that we have used time and again in these live lessons. So in any kind of regression model, we're predicting a specific numeric value. In this case, the outcome that we're predicting is forgetfulness. Another example of a regression model would be predicting the sales of a product or the future value of an asset like a home or a stock price. The other main category of supervised learning is classification. There's multinomial classification, where we try to predict whether a given input, in this case an image, so a handwritten digit, we're predicting whether a given image belongs to one of the 10 possible classes. So is it a 0, a 1, a 2, a 3, all the way through to is it a 9? So there's 10 possible classes that a handwritten digit could fall into. Another example would be the ImageNet data set. So this is a huge online repository of millions of images, and those images fall into 21,000 different classes like Yorkshire Terrier and Great Dane and so on. And so you have an image as your input x into the model, and then you try to predict which of the 21,000 classes that image belongs to. Alongside multinomial classification problems where we have many potential classes that we're trying to categorize our inputs into, we could also have binomial classification problems where there are only 2 classes. So we could have a movie review sentiment predictor where, based on the text of a movie review, we predict whether the review is a positive one or a negative one. We could also have a binomial predictor that takes in images of fast food and predicts whether it's a hot dog or not a hot dog. So when we have a binary classifier, most often that classifier will provide us with a probability output ranging from 0 to 1, indicating the model's confidence that it thinks a given input belongs to one category or the other. So if 0 means that the classifier is predicting that the fast food image is not a hot dog, and 1 is a prediction that it is a hot dog, then the closer the model's probability output is to 1, the higher the model's confidence that that fast food image is a hot dog. Likewise, the closer that its prediction is to 0, the more confident the model is that that image is not a hot dog. And in this paradigm, we somewhat arbitrarily tend to put this halfway point of 0.5 as the cutoff between whether a binomial classifier input belongs to class 0 or class 1. There are several problems with calculating accuracy at this single, somewhat arbitrary threshold. For example, this doesn't reflect model quality at all other points in the output distribution. So if you had this output here and this output here, and there were the same number of points to the left or to the right of the orange threshold bar at 0.5, but with this second model, way more of the predictions are right down at the bottom or right up at the top relative to our first model, this model, even if there's the same number of points on each side of the orange line, this is clearly the better model. This model is much more confident about its predictions, assuming that its predictions are just as often correct as this first model. So there's one problem with having accuracy at a single threshold. Another problem with having accuracy at a single threshold is that it's so weird around this 0.5 mark. So if the correct y is 1, so let's say it is a hot dog, and our model has a prediction of 0.49, so it predicts at a point right here, then that answer is 100% wrong. But if our model were to predict just marginally higher at 0.51 here, then that would be 100% correct. But in either case, it's really not very confident that this is not a hot dog or a hot dog. And so there's another silly quirk about having accuracy at a single threshold. And further to that point, having this single threshold means that a prediction of 0.51 that something is a hot dog is considered just as correct as something that's a 0.99 or even a 1.0. And so again, this is clearly a limitation of this single threshold. The most common solution to this single threshold problem is to use a metric called the area under the receiver operating characteristic curve, or the ROC-AUC metric. In order to calculate the area under the curve of the receiver operating characteristic, this requires integral calculus. So we'll get to that integral calculus in a moment, but first, let's show how we create the curve.